Welcome to the AI Research Roundup. I'm Alex. Today we're diving into a paper from May 6, 2025, Absolute Zero, Reinforced Self-Play Reasoning with Zero Data. So the core idea is an AI model that, it teaches itself. It proposes tasks, learns by solving them, all without any human-created data. The paper introduces the Absolute Zero Reasoner, or AZR. This system uses reinforcement learning with verifiable rewards, meaning it learns from outcome-based rewards, like a code executor checking its work. And impressively, this Absolute Zero Reasoner, despite using zero external data, outperforms models trained on thousands of human examples. It's great to see they also released the implementation. So over on GitHub, in their Absolute Zero Reasoner repository, you'll find, the core training code, some initial seed datasets, and scripts to actually run the self-play process they developed for this. This self-play, as we mentioned, is key to how the Absolute Zero Reasoner learns. Alright, so this first figure 1, really drives home the, quote, zero data point. On the left, you see our Absolute Zero Reasoner, marked with a star, using absolutely no curated data. That's human-collected examples, unlike other models shown that rely on thousands. Then, the graphs to the right show its performance improving in both math and coding domains over training steps. Impressively, this performance is achieved despite operating entirely out of distribution, which means the model shows strong generalization, performing well even on new types of problems it didn't explicitly train on. The overall performance chart then clearly shows this Absolute Zero Reasoner, starting from a base model, climbing to surpass the previous state-of-the-art through its self-play learning. Okay, so building on the Absolute Zero Reasoner's performance, Figure 2 here really helps visualize the Absolute Zero paradigm itself and how it aims for less human supervision. On the left, you have supervised learning, which relies on human-curated examples for what's called behavior cloning, where the AI essentially copies human actions. Then, moving to the middle, there's reinforcement learning with verifiable rewards. This lets the AI learn more on its own, but still needs humans to provide the initial set of problems. And finally, on the right is their Absolute Zero approach, where the model itself proposes tasks and learns by solving them, driving its own improvement, all without direct human data input. Right, so this next diagram, Figure 3, gives us a more detailed look at what they call the Absolute Zero Loop, which is really the engine driving that self-improvement we talked about. You can see a central language model, which, interestingly, acts as both a proposer of tasks and a solver of those same tasks. First, the model, in its proposer role, comes up with a new task. This task then goes to the environment, which is the system that checks and validates the task, like the code executor we mentioned. The environment then provides a reward back to the proposer based on the task's learnability. Then, the model, switching to its solver role, attempts to solve this validated task, and it gets another reward from the environment based on whether its solution is correct. This whole cycle of proposing, solving, and getting feedback just keeps repeating, allowing the model to continuously learn and improve itself without any external data. Okay, so Figure 4 here gives us a more granular view of the Absolute Zero Reasoner training process, building on that loop we just saw. We still have the Absolute Zero Reasoner proposing and solving tasks. What's new here is how it specifies the types of tasks, namely deduction, which is like predicting an output given a program and an input, obduction, where it figures out the input given the program and output, and induction, which is about creating a program from input-output examples. You can see the Python environment, indicated by the Python logo, is used to construct and then verify these tasks. The proposer gets a learnability reward for creating good, solvable tasks, while the solver gets an accuracy reward for correct solutions. Then, both these rewards feed into a joint update step. This update uses a method called Task Relative Reinforced++, or TRR++, which is a smart way to help the model learn more effectively from these rewards across all the different task types. Alright, so after seeing the complexity of that training loop and the different task types, Figure 5 shows us something quite, simple. This is the Seed Absolute Zero Reasoner Zero Triplet. It's basically the very first tiny piece of information given to the system to kickstart that whole self-bootstrap propose and solve loop we've been talking about. You can see it's just an input, hello world, a very basic Python function that simply returns whatever it's given, and then the output, which is hello world again. This extremely simple example is all it takes to get the absolute zero reasoner to start generating its own, more complex tasks and learning from them. The paper notes the model could even start without any seed, but this illustrates the approach's flexibility. Okay, so this next image, algorithm 1, lays out the detailed recipe, or pseudocode, for the self-play training of the absolute zero reasoner. It really formalizes that loop we've been discussing. It starts with a pre-trained base large language model, and that initial seeding step, like the hello world example we just saw. Then it goes into a big loop. Inside this loop, there's a propose phase where the model generates new tasks of those types we talked about: deduction, abduction, and induction. These tasks are then validated by executing them, checking for things like syntax, safety, and making sure they give consistent results. If a task is valid, it's added to a buffer. Following that, there's a solve phase. Here, tasks are taken from the buffers, and the model tries to solve them. Based on its performance, it gets rewards. Finally, the algorithm uses reinforcement learning, specifically that task-relative reinforce++ method we touched on earlier, to update the model's internal settings, helping it learn from both proposing good tasks and solving them correctly. This entire process just repeats, allowing the model to continuously teach itself. So after detailing that self-play training algorithm, Table 1 here really shows us the payoff. This table lays out the performance of various models, including our absolute zero reasoner, on a range of pretty tough coding and math reasoning benchmarks, things like Human Evolve Plus for coding and IM for math problems. It compares them using average scores for coding, which they call CAVG, math, or MAVG, and an overall average, AVG. Now, the exciting part is the section Absolute Zero Training with No Curated Data Hours. You can see the absolute zero reasoner, specifically the Coder 7b version, trained with zero external data, achieves an impressive 50.4 overall average. Its coding average is 61.6, even beating models trained with thousands of examples. The little plus numbers also show significant gains over the base models it started from. Those numbers really drive home the point. The absolute zero reasoner demonstrates that it's possible to build highly capable AI models for complex reasoning, like coding and math, using purely self-generated tasks and reinforcement learning, all without a single piece of curated data. This is incredibly exciting because it paves the way for more autonomous and data-efficient AI. That's all for this AI Research Roundup. Thanks for joining me. I'm Alex.